Yeah, so it's now getting recorded. Can you guys confirm if everything's fine so far? Like I am audible and also my screen is visible, right? Okay, great. So today is day 2 of this dynamic programming bootcamp. We've already had one lecture in this series. So before we get started, I would like to know from you guys, how are you finding the series so far? Like if you're finding it good, you can maybe write a +1 in the chat. Or if you're not finding it so good, you can write a 0. And if you're finding it really bad, you can write a -1. So let's see what are you guys feeling so far. Okay, great. So I see a lot of +1s. This is good. Great, great. I also see a plus infinity here, which is really motivating. But yeah, okay. So how many people tried out the homework problems that I had given yesterday? I had given you guys 3 homework problems, and I think all of these 3 problems could have been like done with the concepts that I taught yesterday. So how many people tried it out? You can write a Y for yes and N for no. Like maybe you just read the problem. Okay, somebody's saying they tried out the first problem. Fine. Okay. Were you able to solve that problem? Like, were you able to come up with a state, a transition, and then maybe, code it up as well? How far did you reach on the first problem? The state transition? Okay. So you think could not come up with the transition. Okay, that's fine. But that's a good thing that you actually tried out that problem. So before we, dive into the topics for today's class, I would like to first of all cover those homework problems. Like, I don't want you to, feel left out. Like, I can teach you a lot of concepts, but at the end of the day, what matters is that you're able to solve problems. So we'll start with the first problem, the first homework problem that I'd given you guys, right? So we had 3 problems, right? So this is the first problem, and this is how it goes. Your task is to count the number of ways to construct some n by throwing a dice 1 or more times. A dice has 6 faces, going from 1 all the way up till 6. I mean, the values are going from 1 to 6. And they've given you an example here. If n is equal to 3, that means you want to construct a sum of 3. These are the possible 4 ways of doing this, right? So you're given an n, and you need to find out the number of ways to make n by throwing a dice. So I hope the problem statement is clear. Basically, you have a structure like this, that you have some value n. You want to construct this n by throwing a dice many times. So basically, let's say you can throw the dice and you get 1. Then you get, let's say, 3. Then you get 5, right? So the sum here would be 9. Fine. So you want to construct this given value n, and you want to tell how many number of ways are there to construct it. Also, one thing to notice here is that 1, 3, and 5, and 3, 5, and 1, or 5, 1, and 3, all of these are considered to be different here, although they're summing up to the same value. But if you look at them, these are not like, these are actually different ways, right? So you have to construct n, and the only possible choice of, when you throw a dice is that it can show up with 1, 2, 3, 4, 5, or 6, right? So we're not going to be talking about how do you do it naively. I would directly want you to give me a state now. Instead of thinking about a recursive brute force solution, now we're going to level up a bit, and you guys have to give me a state which can solve this problem. How should I define my state? Do you guys remember how we had talked about that state? You need to divide the bigger problem into sub problems, and every problem should be distinguishable from the other sub problem by the means of some parameters. So how about you guys give me some state to solve this problem and the meaning of that state, which is very important. Okay, so Abhigyan had written in the chat that he tried out the first problem. So Abhigyan, how about you give us the state of this problem? You were not able to come up with the transition, but what about the state? Maybe you can write it in the chat, or even unmute. That's totally up to you. I mean, not just Abhigyan, anybody else can also comment. the number of ways you can get to n. Yeah, that could be a good state. So what you can do is you can define a state like this. You can say dp of I. dp of I is equal to what? Number of ways to make sum equal to I. Does that seem like a good enough state to you guys? dp of I being the number of ways to construct a sum of I by throwing that dice. Great, I see a yes. Good, so this is the state. This seems like a good start. What about the transition? Let's say I am, I want to construct a sum of I, or let's say I want to construct a sum of 10. How do I make a transition here? Okay, one more thing, when you're trying to think of a transition, think of it in this way, that 10 is a subproblem. dp of 10 is a subproblem. How do you relate it to smaller subproblems in the form of an equation? So what would you do here? dp of 10 is equal to, you have to give me a transition here. Okay, so if you're standing at 10, what are the possibilities? How can you reach 10? Let's say you had 9 and you got a, you threw the dice and you got a 1 here. Another way could be that you have an 8 and you threw a dice and you got 2. Another way could be that you have a 7 and you got a +3. And another way could be that you have a 6 and you got a +4. Another way could be that you had a 5 and you got a +5. And another way, like this could be this, that you have a 4 and you got a +6. We have 6 possible ways, right? Okay, great. Somebody has written that dp of I is equal to, dp of I is equal to sum of dp of I minus k, and k going from what? K is equal to 1 going all the way up till 6. Because look at it this way. You have I. How can you reach I? You can reach it from I minus 1 in one way. I minus 1 in one way. Then you can reach I from, you can reach I from I minus 2 in another way by throwing a dice and getting a +2. So does this transition seem good enough to you guys? Somebody's saying 5 only. Why should we take 5 only? The dice here, it has been written, it has 6 faces, right? So we should be going from 1 to 6. You can construct I from what values? You can construct it from I minus 1, I minus 2, I minus 3, I minus 4, I minus 5, and I minus 6 as well. Because you can get a +6 at I minus 6. Right? So what do I write here? Let's see. Let's try to update these values. State is what? State is dp of I is equal to number of ways to get sum equal to I. Right? Sum equal to I. And the transition is what? dp of I is equal to dp of I minus 1 plus dp of I minus 2, so on up till dp of I minus 6. Does that seem fine to all of you? We have a state and we have a transition. Now, what about the final subproblem? What does the question want us to solve? What do you think the question wants us to solve? It wants us to tell us the number of ways to get n. So where would that be stored? It would be stored in dp of n. Correct. Very good. So our final subproblem will be what? It will be dp of n. Okay. So Abhigan, you came up with a state and you also came up with a final subproblem. So that's like a good thing that you've done. You could not come up with a transition, but now does this transition seem fine to you? Are you able to understand this? This is very similar to Fibonacci numbers, like finding the nth Fibonacci number. Okay, you couldn't get around double counting. So if you look at this problem, we're not concerned about double counting. Like 1 plus 2 and 2 plus 1 are the same thing. So you didn't have to care about double counting. Okay, so before we move to the next problem, let's try to quickly code it up. Okay, so we have, let's have a function int number of ways, and you pass it an integer n, and it gives you the number of ways to construct n by throwing a dice. So what we can say, if n is equal to 0, can I say that the number of ways to construct 0 is just 1? Constructing a sum of 0. That's 1, right? So I return 1. And what do? I have to follow a memoization. So I'll say if I can have a DP state in DP n plus 1, because we need n also, DP of n as well, filled with -1 initially to depict the state hasn't been calculated before, right? So what do I do now? I say if DP of n is not equal to what? Is not equal to -1, then you return DP of n. Now, after that, what do? We know that this state hasn't been calculated, so we need to calculate it. So what we'll do is this. Int I is equal to 1, I is less than equal to 6, I plus plus, and we'll say, first of all, we can say DP of n is equal to 0, and then we can sum it up. So DP of n is equal to plus equals to, we can say number of ways, n minus I, and then at the end, we can return DP of n. Okay, we also need to handle one more thing, which is that if n is less than 0, tell me, can you see that we can also get into this case where n is less than 0? When we are calling this function from here, we can get into this state as well, right? When n becomes less than 0. What do you think I should return here? Is there a way to construct a sum of less than 0? No, there isn't, right? So we should return what? We should return 0, because we don't have any ways to construct that, right? All you have to do is think of the function, like what exactly is the function telling you, and then you need to make some base cases, like where exactly can your function go wrong, right? And after that, like it's just simple memoization. You check whether the state has been calculated or not. If it has been calculated before, you directly return it. Otherwise, you calculate it and then return it. So is this clear to everyone, this code? Any doubts in this? All we have to do is this. See out number of ways, and this is what we have to do, right? So yeah, I think this is good enough. We have a state, we have a transition, we have a final subproblem. Now for the next problem, you guys will have to give me a state, a transition, and a final subproblem. Okay. Okay, before we move to this problem, first of all, tell me this. If I give you a state, if I give you a transition, and if I give you the final subproblem, will you be comfortable in coding it up on your own from this point? Like I give you a state, I also give you a transition, and then I give you a final subproblem. So will you be able to like code it up recursively? We're not talking about the iterative implementation right now, but I hope you guys will be able to code it up on your own, right? So what we'll do is for the next two problems, this one, problem 2 and problem 3, we're not going to code it up. We are only going to talk about the state, transition, and final subproblem. And as a homework, you can code it up on your own, right? I think that should be like a good enough exercise here, so that you get to do some practice on your own, right? So let's talk about this problem now. So you have this problem which says consider a money system consisting of n coins. Each coin has a positive integer value. Your task is to produce a sum of money x using the available coins in such a way that the number of coins is minimal, right? For example, if the coins are 1, 5, 7 and the desired sum is 11, an optimal solution could be 5 plus 1 plus 1, which requires 3 coins. Okay, tell me one thing. If I have to construct a sum of 11 and I have these choices 1, 5, and 7, can you construct this value of 11 in some other way as well, instead of following this 5 plus 5 plus 1? And if you can, write it in the chat. Okay, perfect. Somebody has already written 7 plus 1 plus 1 plus 1 plus 1. Great, that is also possible. And somebody has also written 11 once. So that's also a good solution, right? So you guys understand the problem, right? We have to make the sum of x using minimal number of coins. Although we have a lot of ways to do it, we have to find out the minimal, the way which uses the minimum number of coins, right? And if it is not possible, we have to return a -1. Fine. Okay, so let's talk about it. Okay, think about a state now. What do you guys think would be a good enough state? Like we have to, basically, we have to construct a sum of x, and we have choices of coins. Choice of coins. And there are n choices available. in terms of coins. Think of a state here. Okay, what is the biggest problem that you have to solve? First of all, tell me what is the biggest problem. The biggest problem is that you have to find out minimum coins to make sum equal to x. This is a big problem, right? Let's say I give you a problem where you have to tell me the minimum number of coins required to make a sum of y such that y is less than x. So first of all, tell me whether solving for this subproblem where we have the sum equal to y is better than solving the problem where sum is equal to x or not. Like, which is easier? If I tell you y is less than x and you have to construct a sum of y, and in another problem I tell you you have to construct a sum of x. This is the first problem. This is the second problem. Tell me which is easier to solve. The first problem, right? So that's how you can think of a good state. Whenever you are given a problem, try to think of the biggest problem that you have, and then try to think of smaller chunks, right? So now think of a state here. Okay, somebody has written dp of I is equal to the set of coins that give I. Okay, is it the set of coins that give I, or is it the minimum number of coins required to make I? Great, somebody has written minimum. So that's good. So now you guys get the state, right? dp of I, you can make a state like dp of I is equal to minimum number of coins to make sum is equal to I, right? Great, now we're doing good. So what about a transition now? You have a set of choices. Okay, before that, do you guys understand that in the previous problem, if you had to make a sum of n, what were the choices? You had n minus 1, you had n minus 2, you had n minus 3, n minus 4, n minus 5, and n minus 6. But here, do you have like these discrete choices, or do you have like some random choices? Like you have coins, the value of the first coin could be 10, the value of the second coin could be 5, the value of the third coin could be, let's say, 12, right? You have these choices. Let's say you have just four choices, these four choices, 10, 5, 12, and 11 in terms of the coin. So now tell me, if you have to construct a sum of n, what will it be dependent upon? Like, what are the four choices that you have now? From where can you get n? You have this. These are the denominations of the coins. You have 10, you have 5, you have 12, and you have 4. And now you want to make a sum of n. Okay, you want to solve for dp of n. What is dp of n? dp of n is the minimum number of coins required to construct a sum of n. So tell me, what is this value n dependent upon? Like, what are the other sub problems that it might be dependent upon? From where can you reach n? Somebody is saying total sum. Okay, somebody has written minimum of dp of I minus k plus 1, where k is equal to the denomination. Exactly. So very good, Abhigan. You're doing great. For people who could not understand this, I mean, just look at it this way. If you have n, can you construct n from n minus 10 by using just this one coin? You have n minus 10 as a subproblem, and from n minus 10, you add plus 1 and you get n directly. Can you do that? Like just adding a plus 1 here. Similarly, if you have n, and like if you have n minus 5, can you go from n to from n minus 5 to n in just one step? Similarly, you can go from n minus 12 in just one step to n. And similarly here, from n minus 4, you can pick up the coin with denomination 4 and you can reach n in just one. So what do you think will be the dp transition now? Like I told you guys, for thinking of a state, think of the biggest subproblem that you have, then think of smaller subproblems. How do you think about the transition now? Again, think of the biggest subproblem and try to represent it in terms of smaller subproblems through a relation. So what do you guys think will be a relation here? DP of n will be what? You have 4 choices, and in every choice you add a +1, right? So what do you do here? You can just say, first of all, add +1 plus minimum of what? Or what you can do is like represent it like this, in fact. Minimum of DP of n minus k +1. You go for all the denominations that are available to you. You can represent it like n minus ki. So if let's say you had m denominations available with you, then how many choices are you considering? If you have m coins, how many choices are you considering to make a sum of n? You have m denominations. How many choices do you have here to construct n? You have m choices, exactly, because that's how you can relate it to smaller subproblems. Fine. So in this case, like when you say dp of 10, dp of n, when you have to construct for this dp of n and you have this example, what would you say? You will say minimum of dp of n minus 10, comma, n minus 5, comma, dp of n minus 12, comma, dp of n minus 4. And at the end, what you'll do? You'll do a +1 because you're using one denomination, right? So is this concept clear to all of you? What we've done here, like this transition? The state, the transition. And what is the final subproblem? If I give you that x is the sum that you have to construct, what is the final subproblem? dp of x. Perfect. Right. So let's just write it down here in the slide so that you guys have some idea when you're going through these slides. We have dp of, let's say, k is equal to minimum coins required to make sum equal to k, right? And here what you do, the transition is dp of k is equal to 1 plus minimum of, and you have a lot of choices here. So you'll say dp of k minus coins I. Like you can put it like this, coins I. And you can represent it like this, that I is going from, if you're considering zero-based indexing, then you can say this, n minus 1. Right? And what is the final subproblem? dp of x. According to this problem statement, we have to construct a sum of x, and n is the number of coins that you have. So is this clear? Okay, somebody has written why the +1. Oh, right. Let me talk about that. So let's say you want to construct n, okay, and you have this sum available already, n minus 5. Like you know that in order to construct n minus 5, you require how many steps? You require, let's say, 10 steps. You require 10 coins to construct n minus 5. Now let's say you have a coin of denomination 5. If you add one coin here of denomination 5, you'll get n, right? But if you had to, like, use 10 coins to construct n minus 5, you will have to use 11 coins now to construct n, right? So if you had to use 10 coins here, you will do a +1 to make, because you're using a coin, right, at this step. So is this clear to all of you? Okay, great. So before we move ahead, here you'll have to tell me, you guys understand the state, you guys also understand the transition. Tell me, what is the time complexity of this problem? And how do you define the time complexity? The time complexity is defined as number of states into transition time for each state. For each. So tell me, what are the number of states here? Look at this problem. We are saying that we have this DP state. How many states do you have? Perfect. Somebody has written X state. So the number of states are X. And what is the transition time for calculating just one state. Look at this. Look at this formula. We will have to iterate from 0 to n-1 over all the coins. So people are writing m, but in this problem, the number of coins given are n actually. So I am assuming that you're saying n here, right? When you're saying m, right? Okay, great. So yeah, you have states being x, and the number of coins or the number of choices are n. The time complexity will be what? N into, or in fact, x into n. Xn. This will be the time complexity. What will be the space complexity? What do you think? Just look at this DP state and it should be very, very clear. What is the space complexity here? Order of x, perfect. Okay, so now you guys are doing good. That's good. We're done with two problems. Let's talk about the third problem. And let's see if you can come up with the state and transition and the final sub problem much faster in this problem. Let's see. So it's like kind of the same problem, but instead of finding the minimum number of coins required to construct a sum of x, you need to find the number of ways to do it. Basically, in the last problem, we were trying to solve for dp of x, where dp of x was the minimum number of coins to make a sum of x. Here we have to say, I won't give out the state directly, but here we have to find out the number of ways to construct that value x. All right. So let's say I give you a denomination. Again, we have these denominations. We have 5, then we have 10, then we have 12, and then we have 4. So now, what is the biggest problem? First of all, let's solve it very strategically. What is the biggest sub problem that you have at right now? What are you solving for? You have to tell me the number of ways to make sum equal to x. This is what you have to solve. This is the biggest problem that you have. So think about it again. Like if you have to solve for x, you want to construct x, and you have these denominations. You have 10, 5, 12, and 4. What are the number of ways to form x? Right. So if you have x, what are the number of ways to construct x here? When I tell you that these are the denominations available to you, can't you construct x from x minus 10? Give me a yes or no in the chat if you can construct x from x minus 10. Yes, you can. What about x minus 5? Yes, you can. Then x minus 12. And then x minus 4. These are the only possible 4 choices that you have. When you want to construct x and you have certain denominations given to you, these are the only 4 choices available, right? So can you give me a state now? Give me a good enough state. dp of I being the number of ways to form I. Perfect. dp of I is equal to number of ways to form I. Okay, what is the transition here? You will say dp of I is equal to nothing but summation of dp of I minus k, where k is any denomination available to you. Perfect. Somebody has written dp of x is equal to dp of x minus 10 plus dp of x minus 12 plus dp of x minus 5 plus dp of x minus 4. Great. That is exactly what the state will be here. Right? So is this making sense to everyone? Tell me also the final subproblem. dp of I is equal to number of ways make sum equal to I. Transition is dp of I is equal to sum of dp of I minus k, let's say kj. You have j going from 0 to n minus 1 because n is the number of coins available to you. So what is the final sub problem? Look at the problem. What do you have to find? The number of ways to construct x. So what will be the final sub problem? dp of x, right? Yeah. Okay. And again, the time complexity and the space complexity remains the same because we look at this problem. This was pretty much the same thing. Here we were, okay, in problem 2, we were finding out the we were finding out the minimum number of coins required to make a sum of x. But in this problem, what are we doing? We're finding the number of ways to construct a sum of x. Can you give an example where the state is different from the question asked? Yeah, so we'll be, we'll be solving a lot of problems. These were just 3 problems that I had given you as homework yesterday. And these were like kind of the most easiest problems you could come across in dynamic programming. But yeah, with the knowledge that I had, given you in the previous class, these were solvable on your, you could have done them on your own as well. But we will be getting into harder problems. Don't worry about that. Like I've told you, after completing these 7 lectures, you will be in a very good position to tackle any problem that is as tough as a 1900 rated problem on code courses. Right. So are we good to go? Are we good to start with the actual content of this class? Will you be able to code all of these 3 problems on your own? The 3 problems that you've discussed here? Okay, before we move ahead, one more question. Were these 3 problems very, very similar to each of them? They were, right? What is J in problem 3? So J in problem 3 is nothing but I have used an index, like an iterator, which will iterate on all the coins that I have. So I can say not ki, but coins of J, basically. J is denoting the index in the coins array. We are iterating on all the coins available to you. Fine. Okay. So now let's talk about this thing, which is recursive versus iterative DP. Okay. So first of all, tell me all the problems that you've solved till now. We have solved, I guess, how many? 6 problems we have solved till now. Tell me, were all of them, did we solve them iteratively or did we solve them recursively till this point? We solved all these 6 problems recursively. Okay. But now you will be able to appreciate, using an iterative approach over a recursive approach much better, because now you will be able to understand. You've already coded up these problems in a recursive manner, but when you do them in an iterative manner, you will see how an iterative approach is much better compared to a recursive approach. Okay. So first of all, tell me, if I were to tell you that this entire problem that we've done recursively just previously, if we convert it to an iterative form, so will there be any stack space there? Like when we are doing a recursion, we are creating a stack space, right? We have a function over another over another. So that's creating a stack space. Will we have to create a stack space when we are doing it iteratively? Yep, exactly. We won't need any stack space. We will not be, doing it recursively. It will all be there in just one function. When I say iteratively, I am not calling a function inside another function. I am saying that in a single function, I'm going to be doing everything. And if I tell you that the time complexity somehow remains the same in iterative and in the recursive way, can you say that the iterative way will be much faster than the recursive way? If I tell you that time complexity is same, but now you're not constructing an entire stack of functions, it will be faster and it will also consume less memory, right? Okay, let's talk about it. How exactly am I saying this? Look at this first problem. This is how we coded up, right? This is how we actually wrote the code for it. Okay. So this was the recursive manner of doing this thing. Let's do it in an iterative way. Let's remove this and let's have this function void solve. And in this function, I have an integer n, and I want to find number of ways to make a sum of n from dice throws. This was the problem, right? So what is our DP of I? DP of I is number of ways to make sum equal to I. That was our state. And our transition was very simple. Our transition was DP of I is equal to DP of I minus 1 plus DP of I minus 2, so on, plus DP of I minus 6. This was our transition. And our final subproblem was DP of n. This is what we were doing. Now tell me one thing, can I do it iteratively? Can you guys think of an iterative way to do it? Is it obvious or is it not obvious? What do you guys think? If I give you a state, if I give you a transition, and I also give you the final subproblem, can you code it up iteratively? Yeah, what we can say is we can start with DP of 0 being equal to 1. Because the number of ways to construct a sum of 0 is what? Is 1. And then we can directly start from int I is equal to 1, I is less than equal to n. And we'll say, we'll iterate on the dice throws. And we'll say that first of all, DP of I is equal to 0. The number of ways to construct I, and then we'll say DP of I plus equals to DP of I minus j. And we'll also check if I minus j is greater than equal to 0. We do this, and at the end, we just say C out DP of n. Is this making sense to everyone? Like the first thing is that DP of, okay, somebody's asking why DP of 0 is equal to 1. You tell me how many ways are there to construct a sum of 0. You have to throw a dice, and I mean, you can throw it any number of times. Now, if you want to construct a sum of 0, will you throw any dice? You will not throw any dice. So there is just one way to construct it, right? Okay, perfect. Now, is this part clear? That we are iterating from 1 to n, and for every index, I am calculating its DP value by iterating on the dice throws. This thing. I am checking for every possibility in the dice throw, and then I am adding the number of ways. This was exactly what you were doing here. DP of I is equal to DP of I minus 1 plus DP of I minus 2, so on up till DP of I minus 6. So I hope this is clear to everyone, like what we've done here. Okay, tell me one thing. Look at the recursive code and look at the iterative code and tell me which is which looks cleaner and which looks easier to code as such. Like not the thinking part, but just the coding part. This is the iterative way, and this is the recursive way. Somebody is saying iterative. If I give you if I give you how do you have to code the iterative DP, then it is much easier to code the iterative DP, right? If I give you the idea. Before the idea, I'm not saying that the idea to get to an iterative way is much easier than getting to a recursive way. But if I give you the idea, then coding an iterative, coding the problem in an iterative way is much better, right? We are not having any recursion. We are not having any stack space. Here, it's like a lot of functions being called, like one function inside another, right? And also one more thing. Do you guys see that in the recursive manner, we were having to check whether a state has been calculated or not? This was one more thing in the recursive way of coding it up. We had to memorize it. What I mean by that, you need to check whether a state has been calculated before or not. Do you have to do it in case of iterative? Like, are we doing that -1 thing anyway? Checking for -1, anything like that? Exactly, that's my point. Now tell me one more thing. First of all, it should be very obvious that the iterative way of coding is much faster to code as well, and also much faster when it comes to the actual runtime. This recursive code will take much more time than the iterative code, because we have a lot of stack space here, like we are calling one function inside another. So that's like a lot of memory overhead and also like time overhead. But here it's like this one function, we have two for loop. Fine. So this point should be clear to you that an iterative way is much faster when it comes to the runtime. So I should just write it here, faster runtime, and here also faster runtime. Okay, now tell me one thing. Okay, people are writing no. No for what exactly? Is this part not clear? Like the iterative way would be faster than the recursive? Okay. Right. Apart from this, tell me one thing here in the iterative code. Can you see that I specifically wrote this for loop starting from 1 to n? Will the solution work if I reverse this thing? If I write the first for loop from n to 1, will this work? Why will it not work? Understand this. When I said the iterative way is much easier to code and it runs much faster in a much smaller runtime than the recursive way, I did not tell you that it is actually difficult to think of an iterative solution than a recursive solution. And I'll tell you exactly how it is kind of difficult. If you represent this DP array like this, can you see that any state, if you are saying DP of I, what are the states that it is dependent on? Is it dependent on the prefix state or is it dependent on the suffix state? According to this transition, is my state dependent on states in the prefix or is my state dependent on the states in the suffix? The prefix states, right? So it's very obvious that I will have to first of all calculate these states in order for me to get the right result for the state. But tell me one thing, was I concerned about this when I was coding it in a recursive manner? Was I concerned about the order of for loops? Was I concerned about what am I passing to the function? Or was I just concerned about whether it has been memoized or not before? So when I say that in a recursive manner, you have to check for that memoization thing, that whether a state has been calculated before or not. In an iterative manner, you don't have to do that, but you have to make sure you don't get into a situation where you are, getting invalid results, and you have to make it, foolproof on your own. You cannot rely on a recursive function. You have to think on your own. So tell me one thing. Can you see that in order to code this problem in an iterative manner, you have to think more than the recursive manner. In the recursive manner, it's very simple. You have a memoization concept. You don't really care about which function you're calling first. But in terms of iterative, it is very important. The flow of states that you're evaluating is very important, right? So would it be correct to say that it is difficult to think of an iterative solution, but it is much easier to code an iterative solution when you've already thought of the idea? Would that be a right statement? It is difficult to think of an iterative solution, but it is easier to code an iterative solution. And it also runs faster than a recursive solution. Would that be a correct statement? Yep. Seems right from experience, yeah. So that's actually a right statement. But anyway, so these 2 points should be clear, that you have a slower runtime in recursive, faster runtime in iterative manner. In the recursive manner, you don't care about the flow of states. You just call some random functions and they give you a result somehow, in some magical way. But in the iterative manner, it's very important to calculate state in a way that your current state, if it is dependent on some other states, they should have been calculated already. Right now, there is one more thing, which is that in a recursive code, you are not evaluating unnecessary states. So when I talk about this point, don't worry about this point so much. This point, you don't have to evaluate unnecessary states in a recursive solution, and you have to evaluate all states in an iterative solution. Don't think about it right now. We will be solving some really hard problems, and you'll realize that in some problems better to code recursively because a lot of states are unreachable. Okay, don't think about it so much. We're not going to discuss it right now, but I will make this very clear with a good enough example. All right, there is one more point in our recursive in the difference between a recursive and an iterative solution, which is that you cannot apply optimizations in recursive code. So I'll give you one optimization, one very simple optimization here, and you'll realize that you cannot use that optimization when it comes to recursive code. Okay, tell me one thing. When I'm saying DP of I, when I'm saying this is my, sorry, let's make some indices. When I'm saying I'm standing here, what are the states that my DP of I is dependent upon? Is my DP of I dependent upon DP of I minus 8? Tell me this. Is DP of I dependent upon DP of I minus 8? It is not. So tell me one thing. If I'm standing here, if I don't need DP of I minus 8, will I ever need to calculate DP of I minus 8 when I'm standing here? I did not need it for DP of I. Will I need it for DP of I plus 1? I don't need DP of I minus 8 when I'm evaluating DP of I. My question is, will I need DP of I minus 8 when I'm evaluating DP of I plus 1? Will my DP of I plus 1 be dependent upon DP of I minus 8? So would it be a correct thing to say that all my states starting from DP of I, they will never be dependent upon DP of I minus 8? All these suffix states in the suffix. That's a correct statement, right? That all these states will never be dependent upon DP of I minus 8. So tell me one thing. Do I need to store that DP of I minus 8 or I can release that memory? Once I reach to, let's say I am looking at DP of 10. Can I release the memory of DP of 3? Do I need DP of 3 to find DP of 10? Look at this transition. DP of I is equal to DP of I minus 1, I minus 2, so on up till I minus 6. I don't need DP of 3 to calculate DP of 10. So can I say that when I'm standing at DP of I, when I'm trying to find DP of I should make sure that all the states starting from DP of I minus 7, so on up till like DP of I minus infinity, I don't care about these states. I don't care about any of these states. So is it required? So in order to evaluate DP of I minus, in order to evaluate DP of I, this point, do I need any state before DP of I minus 6? If I'm calculating DP of I, will I ever need DP of I minus, any state before I minus 6? I will not need it. So can I release that memory? I can, right? I don't care about that memory now. But think about this recursive solution. Can you say the same here? You don't know where the recursive function is going, like which is the order, what is happening. Do you know that in the recursive code? When I'm telling you to find out DP of n, it is dependent on what? It is dependent on n minus I. But if I'm calculating DP of n, can I say that no state will ever be dependent on DP of what? DP of n minus 7 now. Can I say that in a recursive code? I cannot say that. So can you see that coding a solution iteratively helps us to do some space optimization? Although I haven't really talked about how do you clear that memory. So don't worry about that. I will be coming to that at the end of this lecture. I will tell you exactly how to clear that memory or exactly how to store results that are actually valid or actually important. Right? But this should be clear, this point, that in a recursive and in an iterative manner, you cannot apply optimizations in a recursive code. There are some other optimizations that we'll be talking about specifically in the next class. But I hope this point is clear. Can we use a buffer of only size 6? So we'll be coming to this. I have this entire section on state optimization. So this is the point. This is the part where I'll be discussing this. But this slide should be clear to you, clear to all of you now. The difference between a recursive and an iterative DP. So tell me, if you have a choice in a contest, you are giving a code forces round, and you have a choice to code an iterative solution or a recursive solution. What would you prefer? Okay, I see one answer which says iterative. Any other answers? Iterative. Okay, great. So somebody has written iterative if I can. So don't worry. By the end of these 7 lectures, you will be in a very good position to even code up solutions iteratively. And I will give you a very general way of solving all DP problems. And after that, you'll realize that using that general toolkit, you can code it up iteratively, you can code it up recursively, however you like. You will never be, bound by the fact that you cannot think of an iterative solution, because the general toolkit that I'm going to give you guys, it will be valid for recursive and iterative solutions both. Okay, perfect. So let's move to the next slide, which is this slide. So this is one technique that I'm going to tell you guys. It is a general technique to solve any DP problem. You come across any DP problem, and if you follow 4 steps, you can get to a solution to that problem. As long as you are able to think of a state, of a transition, of a base case, and a final subproblem. So basically, what I want to convey from this slide is that after this slide, whenever you get a DP problem, you will have a strategic way to solve it. You will have to think, definitely. I mean, there is no problem in the world that you don't have to think about. You always have to think. You have to apply your mind. But once you're done thinking about that problem, you will be able to you'll have a step-by-step process by which you can code it up and submit it. Right. So let me tell you this very special general technique, and I think a lot of high-rated competitive programmers use this general technique. When you talk about interview preparation, people won't tell you this thing. What people will tell you is that just memorize some states, memorize some transitions, and you'll be good. It works for interview preparation, but when you're talking about tackling any new problem in DP, it is very important to have a general technique to solve that. Okay, so let me tell you about this general technique. What happens here is that you have a 4-step process. You think about a state, then you think about a transition, then you think about a base case. I mean, base case could be one or could be many. Could be many. I mean, you guys get the idea. Think about the base case and then think about the final subproblem. Okay. Tell me one thing. In the 6 problems that we have solved till now, what are the 2 steps or what are the 3 steps that I've always taken care of? Whenever I'm giving you a solution, I have followed. I mean, I've given you three things out of these 4 always in a problem. And what are these 3 things? And I gave you all of these in a special sequence. I did not jumble up the sequence. So what are these 3 things that we have already talked about so far in this series? The state, the transition, and the final subproblem. Good. So do you guys remember that whenever I was solving any DP problem, I first of all asked you for a state, and that's for a reason, because there is like a 4-step process, and I want you to follow that specifically. The second was the transition. Okay, first of all, how do you find the state? How do you find the state? You have a problem. You think of the biggest problem that you have at your hand, right? What do you do then? You try to break that problem into smaller subproblems. And what do I say? Those smaller problems are states. There is one more thing. You also need to be able to, you should be in a position to differentiate between 2 states. So we make use of what? Parameters, right? I think I've written this in the slide. Clearly define the subproblem, clearly understand when you are saying DT of ijk, any some random parameters, what does it represent exactly? Do you guys see that in the problems that you've solved till now, I have emphasized on the fact that whenever you're writing something like DP of ij, you should tell me a meaning for that. I don't know what is DP of ij. You need to tell me a meaning of that. Like, what do you signify from that? So do you guys understand how to find a state now? Like, what exactly is a state? Although it requires some thinking. I am not saying that from just this class, you will be able to solve any hard level DP problem on your own. What I'm saying is that you will have a step-by-step process to think about it, right? So can I say that the state concept is clear? How do you find out a state? Think of this entire problem, break it into smaller chunks, and then define some parameters that could differentiate between two states. Right? So are we all on the same page? Like, will you be able to think of a state of a problem in a problem? Right? Now, what about transition? What did I tell you about transition? Think of the biggest problem again and try to represent it. Think of the biggest problem, try to represent it with some relation in smaller subproblems. Right? This could be one problem, another problem, another problem, another problem. Define a relation. Right? So is the concept of transition also clear? Let me tell you one thing, that once you're able to think of a state now, this state finding is kind of the most difficult part in any DP problem. Once you're able to find a state, the transition follows automatically. Does it not follow automatically? You have a state in your mind, and now all you have to do is think about a way to represent this a subproblem in smaller subproblem. So does the transition not follow automatically once you have a state? Yes or no? Yes, right? Okay, one more thing. We're done with state, we're done with transition. Let's talk about the third step. So have you guys seen that up until this point, I did not talk about the third step so much. Why did I not talk about it? Because up until now, we were always coding recursively. So do you see that I never talked about the base cases, but in this recursive code, I use them. Look at this. If n is less than 0, I return 0. If n is equal to 0, return 1. Aren't these base cases? This is a base case. This is also a base case. Right? So till this point, I never talked about the base case. I never emphasized on it because we were coding recursively. So it was very easy to think about a recursive. It was very easy to think of a base case when we were coding it, on spot, right? But now tell me one thing: if I give you like a general solution, not saying it is recursive, not saying it is iterative, is it not important to think about the base cases beforehand? We have a transition. When we were saying that f of n, like in the problem of Fibonacci, we were saying f of n is equal to f of n minus 1 plus f of n minus 2. You guys remember, right? When we were finding f of 0, I cannot say that f of 0 is equal to f of minus 1 plus f of minus 2. We cannot do that, right? So a base case is very simple. First of all, you have to find the state. Then you have to find the transition. Now, finding the base case is very simple, and I'll tell you how. All you have to do is see where the transition does not apply. Think of the cases where the transition will not apply or will go into some absurd value. And that will give you what? Your base. Right? So tell me one thing, let's talk about some state transition and let's talk about base cases. Think of this problem and tell me what is a base case. Where would this transition not work? This dp of I is equal to dp of I minus 1 plus dp of I minus 2 and so on up till dp of I minus 6. Where will this not work? From 1 to 6. Yeah, that's a good point, but yeah, that's also actually important. Like it will not work from 1 to 6. So my point is, should you define the base cases? Should you define the base cases from 1 to 6? Or should you define a base case like 0 and less than 0? Think of this. If you're saying 1 to 6, you have how many base cases? You have 6 base cases. But if I just define these 2 base cases, like I allow that equation to run for these values, dp of 1, dp of 2, so on up till dp of 6. I allow that equation to run, but I make the base cases like this. I say dp of 0 is equal to 1 because there is just one way to calculate it. And dp of 0, dp of any number less than 0 is equal to 0. Tell me which is a better way. Is the first way of creating 6 base cases better, or is the second way of creating just 2 base cases better? The second way, right? Because we have to code less. But one more thing here is that, if you look at my experience in competitive programming, it's like I have been doing it for 3 years. So I am able to think of these base cases, these transitions, these states very, very quickly. Okay. It might not click to you on spot. Like when you're solving a problem, it will take some time. If you talk about me, I have solved over like 400 DP problems in this journey so far. Now, if you give me any new problem, I will be in a very good position to tackle it. I will be able to give you very good base cases. I will be able to give you very good transitions. But thinking of these smaller things, like somebody here in the audience could have thought that a base case from 1 to 6 is also fine. But what is the problem there? You will have to define 6 base cases. But with experience, you will understand that you can even minimize the number of base cases, but it will come with practice, it will come with experience. So even if you thought that the base cases were 1 to 6, it's totally fine. It's completely okay and it's great. Okay. So will you be able to, let's say you have a state. Will you be able to think of a transition? Give me a yes or a no. If I give you a state, will you be able to think of the transition on your own? Perfect. If I give you a transition, will you be able to think of the base case on your own? Perfect. So now the 3 steps are already solved. What about the final subproblem? What do you think? The final subproblem is actually the simplest part. All you have to do is look at the problem. Look at the problem, see what it is demanding. In this problem, all we have to do is like find out the number of ways to construct n. So DP of n is the final subproblem. Look at the problem statement and look at your state. These are the 2 things that a final subproblem depends upon. You have a final subproblem. There are 2 things that it depends upon. One is the problem statement. What is the problem asking you? And the second is how are you defining your state? So tell me one thing. If let's say there is person 1, and there is person 2. Let's say person 1 defines a DP state like DP of I. I am not giving you some meaning for it, but consider it to be some random, some random problem. And let's say some other person constructs DP of I, j. Tell me one thing, will the final subproblem be both, will it be same for both of them? This one and this one. The final subproblem depends upon 2 things. Let's call it FS. It depends upon 2 things. It depends upon problem statement, and it also depends on how are you defining your state. So tell me whether the final subproblem will be same for this person 1 and the person 2 or not. Let's say I tell you you have a tree, okay? You have a structure. This is the final subproblem. It depends upon what is the problem statement, and it also depends upon what is the state. It depends, like there is a combination here, combination of these 2. So looking at this, don't you see that the final subproblem for person 1 will be different from the final subproblem for person 2? Like the way they are, the way that they're representing it. Right? Is this clear to everyone? Like, how do you define your final subproblem? Perfect. So I think the final subproblem should not be like difficult. Look at this problem. We mutually found out this final subproblem. Similarly for problem 2, similarly for problem 3. Right? So I hope this general technique is clear to all of you now. And first of all, tell me, even before we move ahead, tell me, were we not applying like 90% of this general technique already when we were solving all of these 6 problems that we've done so far? Weren't we already doing it? Yeah, we were already doing it, right? But now from this point, there will be a very formal way, there will be a very strategic way in which we will solve all the problems from this point. Whenever we are solving a problem, now I will ask you for these 4 steps. I will ask you for the state, then I will ask you for the transition, then I will ask you for the base case, and then I will ask you for the final subproblem. If you master these 4 steps, I can assure you that once you're done solving around 50 to 100 DP problems, anybody gives you any new DP problem, you will thank me for this. Whenever you're doing competitive programming, you will realize that DP is kind of the most easiest topic. It will become the easiest topic because now you have a formal way to do it. Do you have a formal way to think about greedy problems? If I give you a normal greedy problem, is there a standard way to think about it? Is there a standard way to think about a graph problem? No, but there is a standard way to think about a DP problem. So can I say that if I already know the steps to solve a problem, it is kind of just implementation now. There is some thinking involved in the initial part, and after that, it's just implementation. Right? So, can we solve some problems now? Should we solve some problems? using this general technique. And also in DP, there are not like a lot of concepts. There is not like a lot of stuff that you can memorize. Once you have a formal way to solve problems, it's just about solving more and more problems, right? So give me a yes or no in the chat if everything is fine so far and we can move ahead. We can solve problems, solve more problems basically. Okay, perfect. So let's solve this problem. And there is also a very strong reason why, I have picked up this problem set. I have been recommending this to people, to everyone on YouTube, to everyone who follows me. I've been recommending this problem set, which is the CSES problem set. And my only requirement from you guys when you're preparing for dynamic programming is that you solve 70% of this section here. Once you're done solving 70% of this section, you'll realize that most new problems that you are solving now will be sort of like a twisted version of one of these, right? So in this entire series, I will try to pick up most problems from here. Right. So how many problems have we already done? We've done dice combinations, minimizing sum, minimizing points, and coin combination 1. So this is one problem that I would like you guys to try on your own. I will give you this problem as a homework. This is one problem that I'm skipping here, and we'll solve these 3: removing digits, grid path, and bookshop. Okay. So what I'll do is I'll just paste the link. I'll just paste this link in the chat so that if you're able to think of one problem, you can move to the next one. Okay. Right. So let's solve this problem now, which is what? Which is removing digits. So you are given an integer n. On each step, you can subtract one of the digits from the number. So you have to tell the number of ways, the number of steps it will, the minimum number of steps it would require for you to make the number equal to 0. Right? That's what the problem statement demands. So for an example, if I have, let's say, if I have 34. So if I subtract 4 from it, what I will get? I will get 30. And if I subtract 3 from it, what will I get? I will get 31. These are the two states, or these are the two possibilities that I have for a, for a number which is equal to 34. How many choices do I have for a number like 234? What about this? How many choices do I have here to remove the digits? We're not basically removing the digits, but we're subtracting the digit value from the actual value. We have 3 possibilities. We can subtract 2 from it, we'll get 232. We can subtract 3 from it, we'll get 231. We can subtract 4 from it and we'll get 230. Right? So tell me how many choices do I have for 221? How many choices do I have for 221? We have 2 choices, not 3 this time, because subtracting 2 will be like kind of the same thing. So if I subtract 1 from it, I get 220. If I subtract 2 from it, I get 219. Right? So is the problem statement clear to you, clear to all of you? Yes or no? We have to find the minimum number of steps to reach 0 from the given number. Okay, perfect. So spend around how much time? 30 seconds. This is not a difficult problem. Think about a state. Spend 30 seconds. Let me just show you the problem so that it makes more sense. Okay, somebody has written dp of I, where it represents the minimum number of steps required for the number I. Perfect, perfect, perfect. Great. So are others able to think about this? Like if I say dp of I or dp of, let's say dp of I only, dp of I is equal to minimum steps to make I is equal to 0. This is our dp state. Is everyone able to follow this? Was everyone able to think about it? And even if you were not able to think about it, is it making sense now? That dp of I will be the minimum number of steps to make I is equal to 0. Right? I mean, if you have, let's say, a value as x, and x could be something like 2, 3, 1, 9, 8. Let's say this is your x. I am saying what is this depending upon? How many choices do I have to subtract a number from this big number? How many choices do I have? I have 5 choices. I can subtract 2 from it, minus 2. I can subtract 3 from it, minus 3. I can subtract 1 from it, minus 1. I can subtract minus 9 from it, I can subtract, and I'll get minus 9. And I can subtract 8 from it, and I'll get minus 8. Right? So is this clear to everyone? If I have a state dp of x, what is this box x dependent upon? How will you find dp of x? I will just go to all of its digits, right? And I will just check for every possibility. And what will I do? Will I take a minimum or will I add them up? Like if I have some possibilities, what will I do? I have this possibility, I have this possibility, this one. What am I trying to do in the problem? I am trying to minimize the number of steps to make x equal to 0, right? So I'll take the minimum of minimum of all of these. Now tell me one more thing. If I have 230, let's say, should I consider subtracting 0 from it? Like if I have 230, I can subtract minus 2 from it. I can do minus 3 from it, and I can do minus 0 from it. But will minus 0 be a valid state? Like will it be a valid transition? I am saying that dp of I is dependent upon dp of I. Isn't that a cycle? Isn't dp of I being dependent upon dp of I a cycle? So if I tell you that you have a cycle, that the state is dependent upon this state, and this state is dependent upon this one, and this state internally is dependent upon this one, can you ever evaluate the answer for this dp? Like this is one state, state 1, this is one state, state 2, and this is one state, state 3. Let's say state 1 is dependent on state 2, state 2 is dependent on state 3, and state 3 is dependent on state 1. Transition should be a subproblem. That's correct. Transition should be a subproblem, and this shouldn't be a cycle. Why should I say that 230 is dependent upon 230 itself? I am trying to find out the answer for 230. This would result in infinity. Like if you continue doing like this, you will go 230, 230, 230. It will like go on for infinite number of steps because that's a cycle, right? So what do you write as transition? If let's say I give you dp of 1, 2, 3, 7, what do you write as transition? Will it not be minimum of dp of 1, 2, 3, 7 minus 1, because we're subtracting 1 from it, 1, 2, 3, 6, comma, dp of, you subtract 2 from it, so you get 1, 2, 3, 5, and you subtract 3 from it, you get dp of 1, 2, 3, 4, and you subtract 7 from it, dp of 1, 2, 3, and 0. And I add what? Will I do a plus 1? Because I'm taking one operation, I'm doing one operation, I'm taking one step. So will I not do a plus 1 in this entire thing to find dp of this? Because we are removing one digit, so we are performing one operation, right? We need to perform minimum number of operations to make 1, 2, 3, 7 equal to 0. So I will say that it is dependent on these 4 states, like the unique digits in the number, and then I will add a plus 1, and I will take the minimum of all of these. So is this clear to everyone? Okay, perfect. So let's talk about things here. Just a minute, yeah. So we are done with the state. We are done with the transition. The transition was very simple here, right? Because we knew the state. What is the state? So now representing the representing a smaller or representing a subproblem, with the relation in smaller subproblems was easier for us, right? Once we had a clear state in mind. Think about a base case now. Where will our solution not work? Our state was clear. Our dp of x, when I'm saying it is a transition, it is what? Minimum of dp of x minus some digit in x plus 1, and the digit should not be equal to 0. That's the only condition for this thing, for this transition to work. What is the base case? Where will this transition not work? dp of 0, exactly. I cannot say that dp of 0 is equal to what? It is equal to minimum of dp of 0 minus 0. I cannot say that. That would be absurd. And plus 1. So you know that dp of 0, it's a base case. But what is dp of 0? Like, how many steps do you need to convert 0 to 0? How many steps will you need to convert the value 0 to 0? You need 0 steps, right? So the base case is very simple here. dp of 0 is equal to 0. Now, what is the final subproblem? Look at the problem statement. What does it want? It wants you to find out the minimum steps to convert n to 0. Look at the state. What is your state telling you? dp of x equals to minimum steps for x to 0. What is the final subproblem now? The problem statement wants you to find out the same value for n being the number given to you. So what is the final subproblem? dp of n. Right, perfect. So let's write it here in the slide. We have dp of x equal to minimum. Minimum steps to convert x to 0. What is the transition? Transition is dp of x is equal to minimum of dp of x minus some digit of x, right? And what? Plus 1. And can the some digit of x be 0? When I'm saying dp of x is equal to minimum of dp of x minus some digit of x plus 1, can this some digit of x be equal to 0? Yes or no? It cannot, right? Perfect. And what about the base case? The base case is very simple. dp of 0 is equal to 0. And the final subproblem is dp of n. So now tell me, can you code this problem on your own? Okay, perfect. Now, is it required for me to tell you how to code it recursively or how to code it iteratively, or can you do it both ways on your own? Recursive should be very clear. What about iterative? Can I say that a state n is dependent upon smaller numbers? You are always subtracting something from n. So the problems that you're solving, the subproblems that you are dependent upon when you're solving for dp of n are smaller than n, right? So will I run my for loop for iterative from 1 to n? Or will I run my for loop from n to 1? When I have this dp state, if I'm standing here, is my state dependent upon prefix states or is it dependent upon suffix states? Prefix or suffix? It is dependent upon prefix, right? So now can you code it up iteratively as well on your own? I've told you the flow. I've told you the state, the transition, the base case, the final subproblem. And I've also told you the flow. The main bottleneck when you have to convert a recursive code to an iterative code is the flow. What if x is less than 0? Okay, that's a good question. Can you ever get into the situation where x is less than 0? If you have a number x, can you ever subtract a number from x such that it becomes less than 0? Think about it. You're always subtracting a digit from x. Can I say any digit of x will be less than equal to x? Is this not the right thing? Right? So whenever you're subtracting digit of x from x, it will always be less than equal to x. So you can never get into a case where x is less than 0. Right? So let's solve one more problem. And are you guys getting the hang of DP somehow now? Or are you not able to understand anything? Why can't greedy work here? Like always subtracting the largest digit from the number till it reaches 0 will give us the minimum steps. Okay, that's a good question. Let's think about it. Let's say I tell you that you have a number like, um, what can we do? Let's think of a case where this will not work. That's a good question, actually. If I give you an x, why should you not always subtract the biggest digit from x? That's a question. And let's see where will this not work. So let's think about some cases here. So let's say you have something like, 91, let's say. If you subtract the biggest digit from it, you get to 82. And if you subtract the smaller digit, you get to 90. From 90, again, you subtract, let's say now you can only subtract 9, so you get to 81. From this state, you can get to what? You can get to 70, 76, no, 74. 74 and 80. Okay, let's think of a case where this will not work. That's actually a good question. For example, somebody is saying 28 gets converted to 20 and then it gets converted to 18. And then what? Yeah, the greedy here would be like, then 18 gets converted to 10, then 10 gets converted to 9, and so on. So it now from this step, it will require 9 steps. So here it will require 10 steps, 11 steps, 12 steps, and 13 steps. And if we do DP of like 28 going from 28 to 26, and then from 26 to 18, we cannot go from 26 to 18. Can we go from 26 to 18? We cannot. Yeah, let's think of a case here. That's a good question. Why will greedy not work? So for a 1-digit number, this should be like, okay, how about we actually code it up and submit it? Because that will give us a wrong answer, right? If I submit the problem here, it will give us a wrong answer and not this one. This one. And it will be, and it will give us a case where this actually failed. Right? Let's look at 27 first. Looking at this, it is always subtracting the biggest number. But I think like I would like to think of a case on my own here without like, submitting it. So let's say we have 31. This gets converted to what? 20, 28. And if I subtract 1 from it, I get 30. So from 28, I can get to 20. And then from 30, I can get to 27. Yeah, this will not work here. 31 is not a good example. But what about 30? Let's say I have 391. I think these cases cannot be found in 2-digit numbers. Yeah, might be. I think for 1 digit, it's very obvious it cannot be found. But for 2-digit also, I think it will not. We cannot find those cases. But there should be some case where it fails. Okay, let's do one thing. Let's code it up. That's a good question, and let's try to address it. Okay, so you have int n, while n is greater than 0, and we're doing a greedy thing there. So what we do is we find out the biggest digit in n. What we can do is we can iterate on it. So we can say string a is equal to, I mean, basically I'm iterating on all the digits of n. This is the character. So if okay. And then from n, I just subtract that maximum digit. So I subtract, I say n minus equals to uh, max digit minus 0. So here I'm converting it into an integer. And I do steps plus plus. So is the greedy idea clear? Like, what have we done here? This part? This should make sense. Right? Okay, let's submit this and let's see if it works. So let me like log in here. Okay, where do we have this code? We have it in c.cpd. Let's take the input first so that we okay, we're getting 5 here. Let's submit it. Okay, we got an accepted verdict by subtracting the largest digit. That's amazing. So I also got a wrong answer here. And what was I doing here? Okay, this was some DP. But yeah, so up until 6 digits, we don't have any case where this fails. So yeah, this greedy solution also works. But do we have a proof of it? Like it will work. So Varun, you've mentioned this approach. Do we have a proof that this will work? Subtracting the biggest digit always. Right now we don't have a proof of it, but we'll have to prove it, right? But what about DP? Do you have to prove anything, or can you assume that the DP state or the DP solution will give you a right answer? That's actually interesting. Like, you know, they have this whole problem in a DP section and they're allowing for greedy solution. So that's actually funny. But what do you think? Like, actually, I couldn't think of the proof of greedy. So I'll tell you what, when it comes to greedy versus DP, that's also a very important point. When should you consider DP and when should you consider greedy? Okay, you have two possibilities, greedy and DP. Tell me one thing, do you have to prove the greedy solution before submitting it or not? Is it a good thing or not? Like, should you not prove it before submitting or before even coding up a greedy solution? You should prove it, right? Yes or no? Before you even code it up, right? So we should prove it. But is there some proof required in DP? Like it's very, very intuitive when it comes to DP. So you don't have to prove anything. So can you see one thing? Although the greedy solution worked here, and you will see a lot of problems like this, where the DP solution also works and also the greedy solution works. So tell me one thing, which is, kind of easier. Is greedy easier or is DP easier? Remember this part, that when you're coding up a greedy solution, it's very important to prove it. Without proving, it's like, you're just, you're making a guesswork here. So in terms of thinking, like in terms of stepwise thinking, which is easier, greedy or DP? It's obviously DP, right? But that was a good question actually, and I would want you to try and prove it as a homework. Although I will try it on my own as well, but I would want you to particularly try to prove it. Not just, say that, the greedy solution works. You should have a proof of it. So try proving it, and I think that was a good question. And we also were able to solve this problem greedily now. So that's great. So let's move to the next problem, which is grid path. So let's read this problem. You have an n cross n grid whose squares may have traps. And you basically want to go from top left to bottom right. You have to find out the number of ways to do this. So tell me one thing, if we didn't have any traps, like if we had a general grid, if you had n here, like n here and n here, you have to go from here to here, like you have to find out the number of ways. What are the number of ways to go from the top left to the bottom right in an n cross n grid? Did we not talk about a formula in the very first class for this? If there are no traps, if you can freely use any cell, what was the formula? It's like saying that you have down d characters, you have n d characters, and you have n write characters, right? You want to make a string with n d characters, n d characters and n r characters. You want to find out as many permutations as you can of this. So basically, you have a 2n size string. You want to place d r something like this. D. You have to find out the number of ways to do this. What are the number of ways? It is 2n factorial divided by n factorial divided by n factorial. That's like a very it must be very clear. Like this must have come at a lot of places when you were solving JEE level problems. But do we have n d steps and n r steps, or do we have n minus 1? N minus 1 d steps and n minus 1 r steps. If you have an n cross n grid, you have to go from 0, 0 to n minus 1, n minus 1. You have n minus 1 r steps and n minus 1 d steps. So what will be the number of ways to do this now? It will be twice of n minus 1 divided by n minus 1 factorial. I mean, this will be n minus 1, twice of n minus 1 factorial into n minus 1 factorial. Is it not the same as combination of 2n minus 2, n minus 1? This thing, twice of n minus 1, its complete factorial divided by n minus 1 factorial, n minus 1 factorial, and this thing. These are same, right? If you didn't have any traps in the entire grid, can you directly say that this will be the answer? If you didn't have any traps in the entire grid, like every cell was free to you, you can use any cell when you are taking a path from the top left to the bottom right? But if you have traps, what is the problem here? You cannot get to those traps. You have to avoid those traps, and you have to find out the number of ways to go from top left to bottom right. So tell me a state that you can think about. You have this grid. There are some traps. These are like, let's make them red. You have some traps in the grid. You cannot step on these traps. You have to avoid these traps, and you have to. What you have to do? You have to take. You have two choices. You can go down or you can go right. So tell me a state for this. DP of ij, where it represents the number of ways to reach grid ij without getting into traps. That could be a good state. So what Varun is saying here is this, that you get to some cell ij and you tell us the number of ways to go from this point to this point. So let's say this was one of the ways, going from here to here. Another way could be like you take one step here, then you come down and you get here. Another way could be like you go here, you take a one step down here and you come here. So DP of ij representing the number of ways to go from 0, 0 to I, j. Yeah. So Krishnam has also suggested this same DP state. So great. So you guys have the idea of a state now. Let's write it. Let's write it on the slides itself. DP of ij is equal to.
Shouldn't the state be from ij to 0?
Sorry, you're saying shouldn't the state be from I, j to 0, 0?
In the diagram, yes.
Okay. So you have some traps. What you're saying is that if I'm saying this is the I, j cell, I mean, aren't these two the same thing? Like, if I'm going from 0, 0 to this cell, I comma j by taking directions of these type, like going down or going right. Or if I say that the problem is from going, I mean, if the problem is like going from I comma j to 0 comma 0 by taking steps like going up and going left, aren't these two the same? Like going from 0 comma 0 to I comma j, or going from I comma j to 0 comma 0.
So 0 comma 0 won't be the bottom right corner.
Okay.
Like, is this
What
an
is the final?
assumption that
Sorry, I'm not able to understand what you're saying.
like
0 comma 0 will not be the bottom right corner. That's correct. Yeah.
no, like I'm asking, like, why is it not the bottom right corner?
Okay. You want us to define a state like this? Like from I comma j, you go to bottom right like this.
Yes.
Yeah, both of them are possible. That's actually a good point. You can define two states. You can say dp of I comma j. Okay, let's do one thing. Let's talk about this first. This case where ij is like dp of ij is like going from 0 comma 0 to I comma j, and we will also solve it according to your way. Like you said, going from I comma j to bottom right. Fine. Let's solve this problem in both ways. So when I say dp of I comma j is number of ways to go from 0 comma 0. Let's increase this to I comma j. Okay, what is the transition here? Like if I'm saying I want to get to this point from 0 comma 0, from where can I come to this point? This point. There are only two choices from where I can reach this point. And what are those two choices? If I am at I comma j, what are the two choices that I have by which I can reach I comma j when I'm starting from 0 comma 0? Good. Somebody has said I comma j minus 1, and the upper direction, which is like I minus 1 comma j. So can I say that dp of ij will be nothing but trying out both possibilities, the summation of dp of I minus 1 comma j plus dp of I comma j minus 1. Can I say this? This is
But
a
the
transition here.
position should not have the trap.
That's right. That's right. We'll talk about that in the base case. We'll talk about where exactly is this transition going to fail. So what did we talk about? We talked about state. We talked about transition. The base case is the point where we talk about where exactly the transition fails. So we'll consider that as a base case, right? So is the transition clear to everyone? dp of I comma j is equal to some basically like dp of I minus 1 j plus dp of I comma j minus 1. Now what is the base case? First of all, tell me if I am standing on 0 comma 0, what are the number of ways to go from 0 comma 0 to 0 comma 0? There is just one way. So can I say dp of 0 comma 0 is equal to 1? Like going from 0 comma 0 to 0 comma 0 is 1. Would this base case be fine? Right? Now tell me one thing, if this 0 comma 0 itself considered, it had like a trap. Can I now say that going from 0 comma 0 to 0 comma 0 is 1? I cannot even move, like I cannot even get to 0 comma 0 because it already contains a trap. So then can I say dp of 0 comma 0 is equal to 1? No. So what I can do is, first of all, I can say dp of 0 comma 0 is equal to 1, and after this, like I'm overwriting, okay, after this I am saying dp of I comma j is equal to 0 when I comma j contains a trap. It contains a trap. Understand what I'm saying? First of all, I'm saying that this is the base case that I'm initializing, but after that I'm saying that go to the entire grid, go in the entire grid, and for every cell that you see which has a trap, say that dp of I comma j is equal to 0. So tell me one thing, if I first of all mark it as 1, will this step not mark it as 0 later on? If I follow these two steps, first I say dp of 0 comma 0 is 1, and then I say go to all the cells in the grid and mark them as 0 when you find a trap on this cell. then will this not overwrite it? First of all, I initialize it to 1, then I go to the entire grid and it will get overwritten to 0. So is this fine? Is this correct? So somebody had unmuted and had asked this doubt, like this transition will not work when you have a trap. So can I say that if I define a base case, then this will work? Okay, great. So what I can do is, first of all, I can say dp of 0, 0 is equal to 1. Then I say dp of I, j is equal to 0 when I, j is a trap. So this is step 1, okay? This is step 1 and this is step 2. Fine. So can I say that this making a base case like this will work? First I do something like this and then I do this. Okay, what is the final subproblem now? According to this state. And for the person who had unmuted and asked this, you will understand now that if you define a state in a different manner, you will get an entirely different subproblem. I mean the final subproblem. So tell me, can you understand the final subproblem here? Looking at the state, we are saying we define dp of ij as the number of ways to go from 0, 0 to I, j. What does the problem statement want us to do? It wants us to find out the number of ways to get to n minus 1, n minus 1. Perfect. So the final subproblem is n minus 1, n minus 1. Let's do one thing. Let's copy this entire slide and paste it again. And now let's talk about that, another state which somebody had suggested, which was to say number of ways to go from I, j to n minus 1, n minus 1. This was the state, right? This which you were suggesting. Number of ways to go from I, j to n minus 1, n minus 1 instead of saying going from 0, 0 to I, j. So now tell me what are the two states that it depends upon. If you want to go from here to here, what are the two possibilities you have? What are the two choices you have? You can go here or you can go here. So can I say my dp of I, j will be nothing but dp of I plus 1, j plus dp of I, j plus 1. Is this making sense, guys? Perfect. Now what about the base case? Now will I say that dp of 0, 0 is equal to 1, or will I say dp of n minus 1, n minus 1 is equal to 1? Look at this base case. This is right now wrong. I am saying this time dp of ij is defined as number of ways to go from I, j to n minus 1, n minus 1. So can I say dp of 0, 0 is equal to 1? Would that be correct? Yes or no? That would be incorrect. So the actual base case would be dp of n minus 1, n minus 1 is equal to 1. And let's should we move this to next page, or let's remove this part. Now you already know what is step 1 and step 2. So let's remove this part. And what is the final subproblem now? Is it dp of n minus 1, n minus 1 or something else? What is the final subproblem now? dp of 0, 0. Perfect. So now do you understand that the problem was same, but we defined a different state. We defined a state in a different manner, and it turned out that the base case changed a little and the final subproblem changed a little. Basically, the transition also changed, but the logic of the transition wasn't changing a lot, right? So is this fine for the person who had unmuted? Like, are you able to follow now?
Can you open that slide? Sir,
this one? Yeah.
In the state, it should be from I, j to 0, 0, I think.
No, we're going from, the problem is to go from 0, 0 to n minus 1, n minus 1.
No, like I had assumed 0, 0 to be the bottom right.
Oh, I see. I am so sorry. I think I actually solved an entirely different problem now. So what you were saying was you assumed this to be like, let's say 0, 0, right?
No, bottom right. Yes.
Okay, so let me tell you one thing. When you talk about competitive programming, the grids are defined in a different manner. This cell is actually 0, 0. And when you go down, your x coordinate increases. So it's like +1 in the x, And when you go here, it's like a +1 in the y. Right? So the actual top left is considered 0, 0, and the bottom right here is considered to be what? n minus 1, n minus 1. Yeah, exactly like array indices. So is this clear now? But now I guess you guys get to, I mean, you would have understood that there are two ways to solve the same problem. Right? So it does not matter what is the state that you're thinking of, as long as it is correct logically, you should go with it. You should not think like, my friend is thinking of a different state, my current state is wrong. Think about a state, try to prove it. Like try to logically think of its transition, logically think of its base case and the final subproblem. If everything falls into picture, just code it up. Right? So are we good at this point, till this point? Yes or no? Okay, perfect. So we have one more problem that we can discuss, and I have two choices here. Like I don't think we have a lot of time. What we can do is we can discuss either space optimization first, and then in the next class the third problem. Or let's do one thing. Let's not solve the third problem. Let me give you this third problem as a homework. Okay? Because we've already done 5 problems in this class. Now you are in a good position to think of problems on your own. So let's directly talk about space optimization instead of this third problem, and I'll give you this problem as homework. So does that work for you guys? Okay, great. What is problem third? Problem third is like yet another CSS problem. So this is the problem. And if you look at my submissions, yeah, it's pretty bad. This was a long time back. We have defined base case dp of I comma j 0. So while coding, when we are in loop and reach dp of I j is equal to, oh, so what you can do is like somebody is saying that first of all, even when we've when we've marked these base cases, we've marked a 0 at some places. When we're actually coding it up, we might even just say that dp of I comma j is equal to that transition value. But my question to you is that when you're doing something like this, you can just check, right, that if at that point if there is a trap, then you don't use that transition. That is actually the main use of a base case, right? Whenever you are actually in the transition part, you check whether you are in the base case or not. If you're in the base case, don't use that transition. That's what we did in Fibonacci, in the grid problem, everywhere, right? We first checked whether we are in the base case or not, even before we went to the transition part. If we found that we are in a base case, we will never run the transition part. So I think that should clear it up for you. So let me just delete the slide from here and I will give you this problem as a homework. Let's talk about this last one concept, which is what? Space optimization. So can you guys understand that, in this problem that we solved, this dice rolling problem, when we were doing it iteratively, we did not have to. Okay, just a minute. How can we initialize the grid? How can you initialize the grid as in? Yeah, you can initialize it with -1. Yeah, that works. You can initialize it with -1. Why? Because the number of ways will never be -1. But tell me one thing, when you're talking about initializing, that is with respect to a recursive approach, right? You will need it when you're coding it up recursively. Will you need it when you want to code it up iteratively? Because in the iterative manner, we talk about this concept of flow of state. We only get to a state when the state it depends upon have been evaluated already, right? So let's talk about this thing, which is very interesting, which is the space optimization concept. And the entire concept is this, that whenever you are getting to a state, whenever you are standing on a state, think about the other state that it depends upon. As an example, in the dice rolling problem, dp of I, what were the states that dp of I was dependent upon? Tell me all the states that it was dependent upon in the dice rolling problem, the first problem from the homework. It was dependent on dp of I minus 1 to dp of I minus 6. That's correct. This is the first step. When you're talking about space optimization, this is the first step. Think about the other states that my current state is dependent upon. Now think about, do we need answers to all the subproblems at all times? When I'm evaluating dp of I, and let's say I'm evaluating in this manner, I am going from 1 to n. I am evaluating in this manner, and I'm standing at dp of I. I mean, I'm standing in the ith index. So tell me, do I need the answer to all the subproblems starting from 1 to I? Or do I need the answer to just some subproblems? Some or all? This is the question. The answer is some. Right. So tell me one thing, like if I just, think about these states like from I minus 1 to I minus 6, these are the only states that I will need the answer of, right? Before that, everything is useless for me now. Right. So that's the second step. Think whether you need all the subproblems at all times. And now the third step is to, just store the relevant states. Right. So what do? Like if you're standing at I, how many previous states do you need to keep track of? How many previous states do you need to keep track of? Just 6 previous states. So is it beneficial to create an array of size n for a DP, like a DP of n, creating an array of size n? Or is it beneficial to just create an array of size 6 and keep storing and keep updating that array of size 6 as and when you calculate a DP state? An array of size n or an array of size 6? That's the question. What should you do? Should you store 6 values or should you store n values? That's great. You should only store 6 values. So can you already see that we're trying to optimize the space? Is the time getting optimized here? Are we optimizing the time here, or are we just optimizing the space by doing something like this? Yeah, only the space. Good. Perfect. So now let's try to code this problem up, which was this problem. Sorry. Yeah. DP of this first problem, which was the homework problem. So let me give you a general way to think about space optimization. What you have to do is think of 2 states. Okay. The first is the current state. Current set of states, and the other set is like the previous set of states. Okay, tell me one thing, in the problem of dice rolling, when you are saying you are standing at I, what are the previous states that you need? You just need dp of I minus 1 to dp of I minus 6. So this is what? This is the set of previous states that you require. Are we all following here? Like this is the set of previous states that you require from dp of I minus 1 to dp of I minus 6. But once we are done evaluating for I, what is the current set of states that we will need? We will need dp of I minus 5. Sorry, we'll need dp of I to dp of I minus 5. This is the set of states that you will need for the next operation. Is this right or wrong? When we are standing at I, when we are trying to evaluate the answer for I, we need these states. We need these states. dp of I to dp of I minus 1 to dp of I minus 6. But when we are trying to when we are done evaluating the state for I, what are the important states that I will require later on? I will only require these states. Because what is the next state that I will evaluate? It will be I plus 1. Will my dp of I plus 1 depend upon dp of I minus 6? Yes or no? Will the state dp of I plus 1 depend upon dp of I minus 6? No, that's correct. So what you can do is you can create 2 arrays. One is the current state, and the other one is the previous state. So let's try to code this up. So you have int n, and you have a vector int previous. How many states do we require? 6. Vector int current, and you say this is also of 6 steps. So tell me one thing, when I'm trying to find out dp of 1, what do I need? I need dp of 0, dp of minus 1, so on up till dp of minus 5. These are the states that I need, right? If I talk about a general transition. Is this correct? Yes or no? But when I'm saying dp of 1 is dependent upon dp of 0, dp of minus 1, what are these actual values? At 0, what do I have? At 0, I have 0. I have 1. There is just one way to construct the value 0. Is there a way to construct value -1? No. Is there a way to construct the other values? No. But the actual array would not look like this. The previous array would look like 0, 0, 0, 0, 0, 0, 1. This is how the previous array would look like, right? Because these are in increasing order. So if I were to write it like this is dp of -5, dp of -4, so on up till dp of 0. So it depends upon these states. So can I say that my previous is nothing but 5 zeros and 1 1? Is this previous thing correct or not? Yes or no? It's correct, right? Now what do? I just say go from 1 to n and you update your current state. Okay. How do you do that? How do you do that? So will you not say that current of, the last value of current will be what? Will be the summation of all the previous values. Can I say that? Okay, first of all this. Can I say for int j is equal to 1, j is less than 6, j plus plus, current at j minus 1, sorry, just a minute. So what we're doing is we're disregarding, we're removing this value from the previous and we are keeping track of these 5 values. So we'll say current of j minus 1 is equal to previous of j. I am updating the first 5 values of current vector. Is this correct or not? What I'm saying is that I don't know about the next value, like I don't know about dp of I. I don't know about dp of I. This is not known. But do I know dp of I minus 1, so on up till dp of I minus 5? Do I know these values? Yes or no? I know these values. So for the current, how is my current defined? Current is defined as going from I minus 5 to I. So it is important that I first of all update the required values. And then what I can do is this. Then I'll say for int j is equal to 0, j is less than 6, j plus plus. And I'll say the last value of current, which is current of 5, is equal to plus equals to previous of j. What am I doing here? I am saying dp of I is equal to dp of I minus 1 plus so on up till dp of I minus 6. This is what I'm doing in this step. Current 5, okay, understand this. Current 5 will be what? Current 5 will be dp of I. Current 4 will be what? It will be dp of I minus 1. So on. Current of 0 will be what? dp of I minus 5. Is this making sense to everyone? I have 6 indices. The last index should contain the actual dp value of my current state. So what will be the final answer? Okay, one more thing. At the end, do I need to do something else? Should I not update my previous? Once I'm done evaluating the dp of I state, should I not update my previous value? What will my previous value become? Yeah, previous is equal to current. That's correct. Now tell me what will be the final answer. When I'm saying, like when I say dp of n, where will it lie? It will lie in the last index of current. That's correct. So you'll say current I. That's right. So is this correct? Is this fine? Are you able to understand? Can we cyclically use just one vector? Okay, that's a good question actually. Can we use this one vector? You can. You can use just one vector, but understand this thing. What will happen when you're using just one vector? You have 5 values, or basically you have 6 values. You have A, B, C, D, E, F. You have 6 values, right? You are telling me that you will remove this A And you will add another value, which will be what? A plus B plus C plus D plus E plus F. This is what you're doing, right? When you're saying cycling. But tell me one thing, what is the time complexity to remove this A from the starting? Is it order of 1 for a vector, or is it order of n? Yeah, that's correct. So that's actually a very good point. You can do it here, because here it's like just order of 6. Here it's order of 6, so this doesn't even matter, right? But if I, let's say, tell you that your state was dependent on k other states, so then can you say that just to remove that one value, it would take order of k steps? Oh, that's nice. But if you're not removing, aren't you constructing the entire vector? You have to remove. That's the point. You are shifting them all. I mean, yeah, even if you're shifting them all, you like if you don't remove anything, then you're constructing everything. So you will have to remove. So there is this other data structure which is called what? DQ. You can look at DQ, and what DQ does is that it can pop from the front in order of 1, and it can insert at the back in order of 1. So using a DQ would be much better than using a vector if you have to pop from the front and also pop from the end and insert at the front or insert at the end. One thing, this is one proper strategy that I've given you. Always think of two vectors and update your current vector with respect to the values in the previous vector, and at the end just update your previous to current. You just have to follow this one strategy. You don't have to think about DQ or removing something or updating anything. If you follow this, I think this should be fine. Right? So is this fine, guys? Were you able to understand the power of space optimization? And can you do it using recursion? Like, can you do it in a recursive code? The same thing that you've done here. No, because the flow of states doesn't really matter in recursion. You are not sure if you're removing something, whether you will need it at the end or not. Right? So I think this should be fine. Space optimization is done. Let's talk about, just one more slide, and let me remove that one thing, this thing. Sorry. Yeah, because we haven't discussed this problem, so let's remove this. But this is one slide. I think this should be pretty easy to follow. So for a Fibonacci number, it only depended on dp of I minus 1 and dp of I minus 2. So how many states do I need to store? How many previous states do I need to store? 2. Perfect. Now this is going to be tricky. If you talk about grid, let's say I say grid, this grid of ij is dependent upon this state, and it is dependent on just this state. So how many states do I need here? When I'm calculating, let's say I'm calculating for this row. Let's say I'm calculating the dp values for this row, and there is another row here, and then there is another row here. Will I need the dp values of this row to find out the dp values of this row? Yes or no? dp of ij is only dependent upon dp of I minus 1 comma j and dp of I comma j minus 1. So while evaluating the states of this row, will I need the states of this row, I minus 2th row? Yes or no? No, right? So can you optimize the space here? Instead of storing all the rows from top to down, just store the last row, and that should do, right? So can we save some space in the grid problem as well when we are doing it iteratively? Yes or no? Okay, great. And what about the dice problem? I think this we've already discussed. So dp I only depends upon dp of I minus k going from 1 to 6. And we have also seen how it looks in the code. This is how it looks. Right, so I think this was all that I had for you guys. And we've talked about 5 problems today. We looked at the homework problems. Although we did spend a lot of time on the homework problems, I would recommend you guys to sort of work on the homework problems on your own, so that we spend lesser time when we're discussing these problems, right? I mean, I do understand that you have your college ongoing and it would be difficult, but trust me, when I give you 2 to 3 problems, it will hardly take around 30-45 minutes to think about them, think about the state and transition. how can we save space? Okay, so how can we save some space in the grid problem? That is your question. So can you see that dp of I comma j? Look at this. Look at this thing. Yeah, this one. Can you see that dp of I comma j is only dependent upon dp of I minus 1 j and dp of I comma j minus 1, right? What I'm saying is that when you're standing in a row, let's say you're evaluating the dp states of this row, what do you need? To evaluate this state, you will need this one and you will need this one. To evaluate this state, you will need this one and you will need this one. But if let's say this is one row, will you ever need the values of this row to evaluate the states of this row? This is I minus 2th row. This is I minus 1th row. This is ith row. To evaluate the dp states of ith row, will I ever need the values of dp of, will I ever need the answers of I minus 2th row? That's the question. No, right? So that's how we can save some space. We don't need all of these rows. We only need just the previous row. Fine. So I hope this makes sense. So yeah, we talked about this very special concept of space optimization. And let me tell you, when you are solving problems on code forces, after a point, when you are solving problems like 1800 or 1900 rated, you will realize that without space optimization, 90% of the problems won't get accepted. And I'll tell you a reason for this. When we talk about time complexity or the number of operations allowed on code forces per second, especially in C++, it's 10 to the power 8. You can do 10 to the power 8 operations in 1 second and that will get accepted. Like basically that's the limit in C++. So if your code is performing, let's say 10 to the power 8 operations, it will get accepted. But the point is you cannot have a memory of 10 to the power 8. This is going to be huge. The largest memory that you can have is of something like 10 to the power 7. It can even go up till 2 into 10 to the power 7 or 3 into 10 to the power 7. But you can never have a memory which is like 10 to the power 8. So tell me one thing, if you have a time complexity of something like n into m, and n into m is going up till 10 to the power 8, can you have a space complexity of n into m in that same grid problem like we discussed? Will it work on code forces? When you submit a problem with the space complexity being order of n into m, where n into m goes up till 10 to the power 8, will it work? It will not work. But with the what do I say? The space optimization, it will work, right? Because with space optimization, what was the space required? We only needed the previous row. What is the space required in that? Order of m. So the space complexity will become order of m. The time will become order of n into m. And also this is like a cool concept for interviews as well. I've seen this in interview problems as well. Like you are required to optimize the space as well sometimes. So space here would be order of m and the time would be order of n into m. So is this clear to everyone, guys? Why is space optimization even required? Because the time can go a little high, but the space cannot always go that high. Fine. There is one more thing which is like, when does this not work? And I think this should be very, very obvious. Don't think about this. Like, what if we need to backtrack? Don't think about this. We'll talk about it. But tell me one thing. If at the end, you had this grid, and the problem that I gave you guys was this: what are the number of ways to go from 0, 0 to n, n minus 1, n minus 1? This was the problem. If we were solving this problem, then storing just the previous row's answer was good enough. But let's say I give you Q queries. The question is not just to find out the number of ways to go from 0, 0 to n, n, sorry, n minus 1, n minus 1. The question is now to tell me the number of ways to go from 0, 0 to x, y, and you have Q queries for it. Q going up till like something like 10 to the power 5. So tell me now, can I disregard the states of the previous row? Like disregard all the rows above my previous row? Let's say I have this state. Let's say I calculate the answer for this row. I have the answer stored. Now let's say some query comes and it demands the answer for this row. If I don't have the answer for this row, can I answer it? I will have to do the entire thing again. So can you guys understand that if I need the answer to all the subproblems, it could be, it could be asked in a lot of different ways in a problem. But if I need the answer to all the subproblems, then can I use space optimization? Yes or no? Okay, perfect. So I think people are saying no. So that's a good sign. So yeah, that is it that I have for this lecture for you guys. I hope you all enjoyed it, and like if you liked it, you can probably write a +1 in the chat or a -1 if you did not like it, so that I get some feedback. Okay, great. So I see some +1s. Perfect. So yeah, I'll end this class now, and the recording will be available on YouTube within an hour, I guess. So I look forward to seeing you in the next class. I hope you're excited, just as excited as I am. So yeah, cool. See you. Bye bye. Thank you so much for attending.